Guys, let's get started. How are you doing? Is your week going all right? Hi. What's your name?
Oh, my name is Max.
Oh, nice to meet you.
Yeah,
You just joined.
Yeah, I just sent you an email, I think, last night.
I see. Yeah. How's your week?
So you're doing all right? What about you?
Pretty good, I guess.
Pretty good?
Yeah, good to meet you again, many of you. And I'm also seeing some new faces. I'll ask for your name a little bit later. So before we start, I want to share with you some of your responses for Monday's workbook, where we asked you to essentially develop some autonomous driving vehicle, and what are some of the key considerations. And this is what you put down. Many interesting ideas. So for one thing, for such a complex system, right, involving all kinds of devices, and digital, analog, or sensors, computing chips, etc., we need to handle this complex interaction between inputs and outputs, right? We have a lot of sensors, proximity, GPS, camera, radar, LiDAR, and all of those will be converted into some digital signals to be processed by your chip. We also need to generate a lot of control outputs, steering wheel, acceleration pedal, brake, signaling, right? And all of those also need to be produced by the digital system. The vehicle will also work in a complex environment, bad weather conditions, raining, snowing, and just night vision limitation. And also there could be just a wide range of situations on the road. It could be unpaved. There could be a graffiti on the sign. There could be some accidents, road closure. And we need to take all of those into consideration. Security and safety is also another consideration that is particularly important for a thing like a vehicle, right, that is driving people at a very fast speed. We need to make sure that anything that we design will work not just right now, but also they will work reliably for the next 5 years, 10 years, and even longer. We need to make sure that at some point, if there's really an emergency that the system cannot handle, it has to return the control to human beings, and then allow us to override any of its control inputs. Practicality, right? These are commercial off-the-shelf devices. Vehicles. So cost is an important consideration. Upgradability, Tesla allows you to essentially pay another few $1,000 and then upgrade your autopilot chip. And that is a way for the company to make more money. It's also to ensure the longevity of the final products. Performance, it has to react quick, right? Latency, the delay between receiving any sensing inputs to producing the output needs to be quick, right? The system has to react fast. And also, these things, the vehicle is running on top of some kind of battery for most of the digital devices. So you need to make sure that it's efficient on the power usage. You cannot put a supercomputer into a vehicle expecting it to get ultra high performance, but at the same time losing all the mileage. And these solutions can be developed at many different levels. So if you are like a system engineer, you could try to design a sensor system that together provides both high visibility and high reliability. There are software solutions. So in general, autonomous driving can be divided into 3 stages. Perception, right, perceiving the environment, followed by planning, right, deciding what to react to on the next time instance, and finally, producing the control outputs. Right? And people talk about end-to-end machine learning, where this entire process is handled by a single machine learning model without any human intervention. Or you could do them step by step and introducing some more hard-coded cases in the middle. Right? Well, it's hard to say which one is better. These are just engineering trade-offs. And there are also chip or board-level solutions. So this is a chip from a Tesla vehicle. And you see they have 2 chips sitting on the board. And these are actually 2 identical chips. They're doing the exact same computation at any time. So you may wonder why we're doing just the same computation twice. Well, that's for reliability issue. Right? To make sure that if one of the chips is malfunctioning, we can essentially identify the error and be able to recompute what has just happened to make sure that I always have the correct results. Right? Again, for a safety and security sensitive system, reliability is of utmost concern. All right. So with that, we're going to come back to our technical talk. We talked about binary numbers yesterday for both positive number in unsigned binary and also negative number represented as 2's complement. So we're going to continue our conversation about negative representation and how to do arithmetics with this 2's complement and another negative representational scheme called 1's complement. So starting with a review of yesterday, this is what we talked about for 2's complement. In 2's complement, positive numbers start with a 0. Negative numbers start with a 1. So positive number is just 0 followed by the magnitude in positive number. Negative number, essentially, you can get a negative representation by first writing the positive number and then flipping out the bits and then add 1 to it. But that's really because of the definition of negative number. There is an actual luggage, a negative luggage that gets embedded to every negative number. So negative 5 is really you try to subtract the positive magnitude from this very big number. And this is essentially 2 to the power of n, where n is the bit width. And then that gives you the negative representation. All right. So OK, let me switch my presentation to the iPad so that I can make some annotations. All right. So this is the definition of 2's complement. You can also think of the same binary representation, 1, 0, 1, 1, in terms of positional weights. So 1, 0, 1, 1 can be interpreted as this one has a positional weight of 1. Next bit has a position, OK. This bit has a positional weight of 1. Next bit has a positional weight of 2. This bit has a positional weight of 8. Right, 8 plus 2 plus 1, that is 11. But since it's a negative number, it carries an actual negative luggage of 2 to the 4. So the magnitude is really negative 5. Right. So you can interpret the magnitude of a negative number by first essentially interpreting it as a positive number, but then including the actual luggage. Any questions so far? All right. Again, to recap, 3 different ways you can look at a negative number. By definition, you subtract the positive magnitude from this number. By the flipping rule, you flip the number plus 1, you get the positive and negative conversion. Or you can treat this as an unsigned number together with an extra negative luggage. Right? All of them will give you the same result, the same interpretation for that 2's complement negative number. All right. So this is another thing we talked about yesterday. 2's complement addition just works. You follow the regular binary addition rule. The result is correct. But it is correct only when you throw away the carry and assuming that there's no overflow. Right? And the question that we talked about yesterday is why are we able to throw away the carry out? And then I have your perspective and also my perspective. So some of these are generated based on your inputs. One way to think about it is really, if you look at the result, right, this number in 5-bit format has 2 leading ones. But if you take away one of the ones, you actually have the same magnitude. So let's say 1, 0, 0, 1 at the bottom, positional weight of 1, positional weight of 8, and this extra implicit luggage of negative 16. Right. So 9 plus 16, which is negative 7. Right? That's what we expect. If you look at that full 5-bit number, you have positional weights of 1 and 8 and 16. And since it's a 5-bit number, the actual luggage would be negative 2 to the 5. So negative 32. And these 4 numbers together also add up to negative 7. Right? Which is saying that if you have like multiple leading ones, you can throw away a few of them without changing the number represented by this binary string. Right? So 5-bit and 4-bit are equivalent in this sense. Another perspective is you can interpret it in terms of positional weights. The negative number, again, for 4-bit, carries a negative 16 positional weights. So if you look at it as an unsigned number, what it really represents in that unsigned sense is negative 3 plus 16 to compensate for the implicit luggage. Right? 1, 1, 0, 1, it's 1 plus 1 plus 4 plus 8, which is 13. That is negative 3 plus 16. That's what unsigned representation means with 1, 1, 0, 1. Similarly, negative 4, if you look at it as an unsigned number, that's 1, 1, 0, 0, positive 12. Right? So every negative number in the unsigned sense is represented by that number plus 16 to compensate for the implicit luggage of negative 16. When you add those 2 numbers together, you're expecting to get negative 7 plus 16. Right? It's a negative number, and you have to compensate it with the implicit luggage. But what you're really getting from those unsigned addition would be -7 plus 32. You added 2 copies of the luggage. So you have to throw away 1 copy. And that's the magnitude that you want to throw away, again, in the unsigned sense, would be 16, which is exactly the carryout. Right? So for that reason, you needed only 1 copy of the luggage. You had 2 copies originally, so you can throw away 1 copy. And that copy will show up as a carryout. So we can formulate the rule as throwing away the carryout, then you get the correct magnitude. Any questions? Yes? The luggage is some implicit magnitude associated with every negative number. So let's say when you show 1011, right? We didn't really say it's a negative number, but since it has a leading 1, we treat it as a negative number. But these 3 positions of 1s, they have magnitudes of 1, 2, and 8 respectively. Right? That's all positive. But to interpret it as a negative number, we have to implicitly assume that there's some actual negative burden that it carries. And that burden is what I call luggage. Right? -16, you just have to assume it's always there for a negative number, but it's never shown. That is implicit whenever you see a leading 1 at the most significant bit. You know it's a negative number, and then you have to assume some additional -16 to its like unsigned magnitude. Yeah. Any more questions? Yeah, I know this part is a bit harder to understand, right? Like why we're exactly showing away, and then we have this. Now I'm talking about like positive luggage. So it's really looking at the same picture from the opposite angle, in terms of what this binary number means in the unsigned number. Since when we do the binary addition, we're essentially doing unsigned addition bit by bit. So I'm looking at it from the opposite angle. So it might take some time to absorb it, but think more about it, and then we can talk. Yes, I think you raised. Yeah.
I do have a quick question.
Yeah.
So 11001, so that's -7, right? Or is that
1101?
Yeah.
That's -3.
-3?
Yeah.
11001, like the
11001, that's -7, yes.
Okay.
Yeah.
All right, perfect. Thank you.
Right. But again, we're still revisiting addition with an overflow. So overflow could sometimes happen when you add together 2 positive numbers, but in the 4-bit result, you get a negative number. And obviously, that's not correct. Right? You cannot get a negative number by adding together 2 positive numbers. Similarly, we add together 2 negative numbers, both with leading 1s, and then we get a 4-bit positive number with a leading 0. It's also incorrect. And those are, these are the situations where you will have an overflow, like something that has obviously gone wrong by comparing the sign of the inputs and outputs. So let's say if you're adding together a positive number and a negative number, right, you'll never have an overflow. You're getting a little bit closer to the 0, right, closer to the mid of the range. So it will never overflow. It's only when you go a little bit too big on the positive side or a little bit too small on the negative side, that's when you have an overflow. Right? And this is the exercise I invited you to try it out yourself after class. So for 2's complement subtraction, sometimes you can also have an overflow. Again, there are a few cases we need to analyze. Right? Let's say positive minus positive, negative minus negative, right? Positive minus negative, negative minus positive. These are essentially all the cases that could happen. Right? The enumeration between positive and negative operands to subtraction. So positive minus positive, again, you'll never have an overflow. You have more than enough numbers on the negative side to represent the result. Right? So you have this positive number, 0, and negative number. If you subtract 2 positive number, it's going to fall into the same negative number range. And the negative number, OK, positive, positive, no overflow. Right? Negative minus negative. So you're a little bit going more positive compared to the first negative operand. Right? So let's say -7 minus -5. You're really going up from -7 by 5 numbers. So you're moving closer to the center of your range, not away from the center. So you would also have no overflow. positive minus negative, that could be problematic, right? Let's say if I have a very big positive number, and you subtract the negative number from it, which essentially means adding up the magnitude of the negative number, that could produce an overflow, right? So let's say if I start with some number like 3 minus 7, right? I'm intentionally picking a pretty big negative number. This one, essentially doing 3 plus 7, should give you a 10, and 10 cannot be represented within 4 bits, right? So it should be an overflow case. So if we write out those binary calculation, 0011 minus 1001, right? 7 minus negative 7. What you will get is 0, 1, 0, 1 with a with an extra carry out. Borrow out. 3 minus negative 7 gives you almost like a 10, but within 4 bit it's not quite a 10. Right? Within 4 bit, this is a negative number. The magnitude is sort of correct, and it would be correct if you have one additional bit and you put down a 0 over there. But within a 4-bit number, that's an overflow. Right? The result, positive 10, cannot be represented within 4 bits. So this is an overflow. Right? When you do positive, subtract negative, and then it appears like you're getting a negative number, which is definitely incorrect. And finally, negative minus positive. Let's say we do, OK, I'm going to pick a pretty negative number, like negative 6, and then minus 4. And then in binary, they will be written as negative 6 is 5 plus 1, so 1, 0, 1, 0. Right, this is negative 6. And then if you try to subtract 4 from it, 0, 1, 0, 0, you get 0, 1, 1, 0. Right? And this one does not have a borrow out, but it is still an overflow. Right? Negative minus positive, you should get a negative number, but you get a 4-bit positive number. Right? Again, by only checking the signs of inputs and outputs, you can determine the overflow condition. It is when things have obviously gone wrong. Right, so this is also an overflow condition. Right, but you see, one thing worth paying attention to is that in this case, I do have a final borrow out. In the second overflow case, I have no borrow out. So borrow out does not equal the overflow condition. Right? In fact, for 2's complement, carry out also does not equivalent to the overflow condition. You really have to check the signs of the inputs and outputs. In unsigned addition, carry out equals overflow. In 2's complement, that's not the case. Any questions so far? Yeah, just any thoughts? All right. So with that said, that's everything about 2's complement. We have seen how to represent numbers, how to interpret it in terms of positional weights, how to do addition and subtraction, and finally, how to detect overflow. And now we're moving on to the next topic, which is an alternative way of representing negative numbers. It's called 1's complement. As you can see from the name, 1's complement is kind of similar to 2's complement. They only differ by 1. And they differ by 1 on the implicit luggage of negative numbers. So again, for the positive number, 2's complement, 1's complement, even unsigned, they're all the same. 1's complement, positive number has a leading 0, followed by the magnitude, right? Same as 2's complement. But for negative numbers, the kind of implicit luggage is slightly different. Right? Instead of having, let's say, a negative 16 for a 4-bit number, it has an implicit luggage of negative 15. So like 1 above, if you think of it as a negative number, 1 above that number. And the way we can generate negative numbers is by probably first writing down the positive representation and then flip out the bits without adding the 1. Right? In 2's complement, we flip, add 1. We do the positive-negative conversion. In 1's complement, we simply flip. So if you think of it, positive 5 at 0, 1, 0, 1, -5 is exactly 1, 0, 1, 0. Right? Just flip out the bits, you get a negative number. And this is, again, aligns with the definition of 1's complement. So instead of subtracting the positive magnitude from 1, 0, 0, 0, 0, we're now essentially subtracting it from 1, 1, 1, 1. Right? That's 1 smaller than 2 to the power of n. And 1, 1, 1, 1 minus any number is the same as flipping that number. Right? That's by the binary subtraction rule. Right? Do you think this is better than 2's complement or worse? Yeah, Eric. It's worse? Why is that? It's 0 twice, exactly. Well, that's definitely one issue, right? This one, although it has a symmetric range, right? On the positive side, you can go from 0 to 7. Negative side, you can go from 0 to -7. You have 2 zeros, a positive 0 and -0. And that might create a little bit more complexity in handling the numbers. And I say when you're doing comparison, it's not as straightforward as just checking the equivalence of 2 binary strings. You probably also have to handle that special case. It's also worse than 2's complement in terms of arithmetics. And we're going to see that in 1 second. All right. So again, in terms of positional weight, again, you can think of -1's complement number as having an extra implicit luggage. But instead of being -2 to the 4, this is -2 to the 4 plus 1. Right? So -15 in 1's complement compared to -16 in 2's complement. Right? Addition is when issue arises. When you do the addition, binary addition doesn't work right away. You have to make some small tweaks. So let's say if you're adding together these two numbers, 7 plus -4, right? You're expecting to get 0, 0, 1, 1 out of it. But when you actually do the addition, you get only 0, 0, 1, 0. And that is off by 1. And for 1's complement, you have to essentially bring any actual carry and borrow back into your first computation result, and then do an additional addition or subtraction step. For 1's complement addition, this is what we call the AND carry. Right? And then we have to bring it back into the rightmost position to perform a correction step. And this is called AND around correction. Right? Indeed, that's what I need. I need to go from +2 to +3, and +3 is the correct number. So I need to do that correction. And it just so happens that we can conceptually think of it as bringing any additional AND carry back into the partial result and then perform an additional addition step. Right? And when you do not have a carry, right, like in the second case, 0, 0, 1, 1, 0, 0, 1, 0, right, both are positive numbers, and the result is just 0, 1, 0, 1. Right? Essentially, unsigned addition just worked. So when you do not have a carry, at the end, you don't have to do the correction step. So this is an extra correction step. Okay, I think I can write it better. Let's see. An extra correction step when you have an AND carry. Again, the question is never about remembering the rules. The question is why it works the way it does. Right? Can you think for a little bit and see if you can figure out why we did this additional correction step? Right? Maybe in terms of positional weights. You don't have to get a perfect answer. I just want you to try it out a little bit by yourself, and then reflect a little bit on how to think about negative binary numbers in terms of positional weights. I'll give you 30 seconds. All right, time is up. Anyone got some ideas. The question is why we took that end-around carry and added back, right? Why do we need this correction step?
You gotta take into account signs like positive, negative.
Could you be more specific? Yeah.
Oh, because I think for onside, you add a 0, 1 to determine if the number is negative or positive.
Mm-hmm.
The two's complement, you flip them, add 1, also to determine if they're positive or negative.
Mm-hmm.
So by that assumption, you move the overflow digit and add them. That's how to determine if it's positive or negative, right?
Well, I mean, if you look at the 4-bit result, 0010, it's already a positive number, and that is correct, right? We add together those two numbers, we expect to get a positive number. So the sign is kind of already correct. And this carry manipulation is a way to sort of like, throw away 16 and then add 1 to it, right? In terms of the unsigned magnitude, right? We are throwing away 16 and then add 1 to it. And those two numbers together gives you sort of like a 15, which is the actual luggage of the negative number. Or the other way to say it is, if you look at -4, right? -4 in the unsigned sense is represented as 1011, so that is positive 13, or essentially -4 plus 15. Sorry, I mean like positive 11, 8 to 1, positive 11. Right? This is how it's represented as an unsigned 4-bit string. And when you do this addition, again, we're always following the unsigned addition rule. Because addition doesn't care about the representational format of the number. It's only 0 and 1 added together according to a specific rule. So when you do that, you expect a positive number without the luggage. Right? You don't need luggage. So this one, the actual one, has a positional weight of 16. So if you throw it away, you're essentially doing a -16. But then when you add 1 back, together gives you a -15. That's how this luggage cancel out with each other through this end-around manipulation process. Right? We're essentially doing two things: throwing away this extra carry and then adding 1 back. Does it make sense?
Yeah, it does make sense.
All right. Right, you can eventually formulate the correction algorithm just by simply saying that end-around carry becomes additional 1 that you need to add it back to the result. But this is actually what's happening. The positional weight manipulation, 2 steps, throwing away 16, adding 1 back, combined gives you the equivalent actual luggage as your negative input number. And on the other side, since we're not dealing with luggage, right, positive plus positive gives you positive, then we don't need a correction step. All right. I think one thing I want to remind you is that in this class, there's always like an overarching theme of duality. When you have addition, you have subtraction. When you have eventually in Boolean algebra, you have a 0, you have a 1. And any theorem for 0 will have a kind of equivalent or dual form for 1. So everything has 2 faces. So when we do one's complement addition, we have an end-around correction step. When we do one's around subtraction, we have a very similar step. Right? That is when you have an and borrow. You need to subtract it from the first binary number that you computed. So if I were to do that computation, 6 minus 5, just positive 1. No and borrow, no correction needed. Another number, 3 minus -1, I expect to get a 4. Right? But what I first got from binary subtraction is a 5. And that is off by 1. I need to bring this and borrow back down there, and then do a subtraction step. Right? One additional subtraction. Whenever you have a carry or borrow, you do an additional step by adding or subtracting 1 respectively. The reason is, of course, for the luggage. Right? But this one a little bit more intricate, so I'm going to skip it. All right. Any questions so far? All right. So 1's complement seems to be a bit worse than 2's complement. So why are we even learning it? This is used in some applications early in the days, I think about like 30, 40 years ago. We have a similar mix of ones complement and twos complement computers, but eventually twos complement dominate. But even nowadays, every IP packet, like when you communicate on the internet, right, a lot of these IP packets that get sent, we're using ones complement in every single of those IP packets. And it's really because of the symmetric property delivered by ones complement. It allows you to essentially do some order agnostic operations. I mean, for example, if you switch the input order, then you don't have to recompute the output order. Output will just be shuffled to produce another valid output without doing the recomputation. And that has some communication and computation benefits. And again, this originates from the fact that complementation is very convenient in one's complement. So for some special circumstances, when you need this kind of complementation properties or symmetric property, one's complement is just a coding method that you can apply. And by the way, I want to remind you that any slides with like a purple header, right? These are like curiosity slides. These are like not the things that you really need to know for exam or for grading purpose, just to provide you a little bit more background and context, right? Give a purpose to what we're learning. Right. So to sum it up, two's complement has an action luggage of -2 to the n for negative numbers. So -16, let's say, for 4-bit number. One's complement has a slightly off luggage by 1, -2 to the n plus 1, so -16 plus 1, which is -15 for a 4-bit number. And you can do negation in two's complement by flipping the number plus 1. You can do negation in one's complement by just flipping the number. For arithmetics, I mean addition and subtraction, two's complement just works. One's complement requires this additional end-around handling, depending on whether you have an end-around carry or end-around borrow. You need to add or subtract 1 from the first computation result. And finally, in both cases, you need to check for overflow. And overflow is simply checked by checking the sign of the inputs and the sign of the outputs. Right? If that obviously does not make sense in terms of whether it's positive or a negative result, then that's an overflow condition. Anything else will not be an overflow. So that's pretty much everything about ones and twos complement representation, addition, and subtraction. Right. Any questions? Before, we're still going to see ones complement, twos complement a bit more, but for multiplication. So getting a little bit more advanced. Right. So that's our next topic, multiplication in unsigned, twos complement, and ones complement. Right. I told you that binary is just the same as decimal, except that we are following binary addition and subtraction rules. For multiplication, it's actually the same. Right? If you think of those as decimal numbers, 111 times 101, this is probably how you would set up the table, right, in this column method. Right? By shifting the multiplicand by a few positions, depending on the value in your multiplier. In binary, it's exactly the same, except that when you're doing this accumulation step, you're following the binary addition rule and the binary carry rule. Right? But other than that, it's exactly the same. You shift the multiplicand depending on the value of the multiplier. This is even a bit simpler than decimal in the sense that the multiplier bits can only be 0 and 1. So you either put down a string of zeros or just copy down the multiplicand. You never have to calculate manually multiplicand times 3, multiplicand times 9, times 7. Right? Those are the troubles in decimal multiplication. So for unsigned binary multiplication, exactly the same as decimal, but simpler. Two's complement, it's a little bit more complex, and that has something to do with the actual luggage. Right? When your multiplier, let's say, has a leading 1, it's a negative number. And again, the multiplication algorithm essentially breaks down the multiplier into a few individual bits and try to calculate some partial products by just jumping down the multiplicand or shifting the multiplicand, and then finally adding them up together. So how can we look at this multiplier in terms of positional weights? What would be 1 plus 4 minus 8? Right? Like a 3-bit number, actual luggage is -8. So what we can do is we can keep multiplicand times 1, add it with multiplicand times 4, and then subtract multiplicand times 8 from it. right? Breaking down the multiplier into a bunch of individual positional weights, and then get those partial products by shifting the multiplicand. And then eventually do a set of accumulation. But at the final step, we're handling this actual luggage, right? It's a negative luggage. So you got to do a subtraction. Right? So if I were to do this calculation, this column gives me a 1. Right? Next column, 1 plus 0, so 1. Next column, 1 plus 0 is a 0 with a carry out of 1. Next column, what do I get? Next column, 1 plus 1, and then I have a minus 1. Right? So I get a 1. And next column, 1 minus 1 is a 0. Right? And then finally, I got essentially nothing minus 0. That should give me a 1. I think this is not quite right. Right? This is not quite right. I should get just a positive 3. So let me see what's going wrong. Oh, I see. You see, this one, just following the binary rule doesn't work. Right? It's not the correct number. And so I'm missing something. Right? The question is, what am I missing? Well, what I'm missing is the numbers over here. Right? Typically, we assume them to be all zeros. Right? But that's not correct in 2's complement. Right? In unsigned, that's right. When you want to extend the number to fit in longer bit widths, you simply put down more zeros. Right? 0 does not change the magnitude of unsigned numbers. But for 2's complement, you got to do sign extension. Right? Remember that 5-bit and 4-bit example I showed you earlier? 2 leading ones, single leading one, they're equivalent. It's really telling us for a negative number, if you want to extend it, right, you got to put down the sign. Positive number, put down more zeros to the left. Negative number, put down more ones to the left. Those are the 3 challenges I highlighted. Right? In general, you have to think about these 3 questions when you do multiplication in any base, right, for any representational scheme. How to do shift, right, shift the multiplicand. How to do extension to fill in these numbers. Right? And finally, how to handle the actual luggage, right, the implicit positional weight that allows you to get a negative number out of the binary representation. Right? These 3 questions are the things that we need to answer. So for 2's complement, just mentioned, the way we do shift, is quite straightforward. It's just shifting zeros. Right? So these numbers are really all zeros. Right? The bottom right corner, that's when we do shift of the multiplicand. We just drop down zeros. If you want to fit this number from a 3-bit number to be a 7-bit number or a 6-bit number, I need to do sign extension. So on the top left corner, I need to put down a lot of 1s. Sorry. I need to put down the sign. So these are zeros, because that second line is all zeros. And next line is a 1. Right. If you are kind of shifting multiplicand, it's non-zero. Right? It's like a negative number, you put down 1. If it's a negative number, put down a 1. If it's 0, just do the sign extension. Right? We're always doing sign extension for this number, this number, this number, respectively. Right? So now if we come back to our accumulation or addition and subtraction step, let's see what we get. Right? 1, 0, 0, 0 gives you a 1. 1, 0, 0, 0 gives you a 1. 1, 1 gives you a 0 with a carry of 1. Right? And next column, 1 plus 1 plus 1 minus 1. Essentially, you get a 2. Right? 2 would be a 0 with a carry out of 1. Next column, 1, 1, 1 minus 1. Again, 2. You get a 0 and a carry. And finally, 1, 1, 1 minus 1. You get a 0 and the final carry. Again, 2's complement. If there's no overflow, we can just throw away the final carry. So this is what we get, and that's exactly 3. Yes? Yes.
So when you did 1 plus 1, so yeah, that's 0. There's a
OK, so the next column has twice the positional weight as the current column.
yeah.
Right? So if this column, so positional weight of 1, of 2, of 4, right? So if you generated 2 over here, that really means 4 times 2, which becomes a 1 on the next column. Right? In decimal, let's say when you have a carry, right, it's like 10 over here becomes 1 on the next column. Over here, it's like 2 in the current column becomes 1 on the next column.
Yeah, so but there's 4 in the next column, right?
But one of them is subtraction.
Oh,
right?
Oh, my bad.
Yeah, the last step is subtraction. So 3 ones minus 1, so it's a 2.
Oh, I see.
Yeah. Yes, Eric.
Would you do it if it wasn't subtraction?
Yeah, if it's not subtraction, if you have 4 ones, you generate a carry to 2 columns away. Yeah. Right. Does it make sense? Right? We essentially parsing the multiplier in terms of its positional weights, and then doing the addition and subtraction step, and then making sure that we're doing the extension and shifting correctly. So I have a better picture over here. Right? Again, shift that multiplicand by depending on the positional weight of the multiplier bit. But if it's a 0, we just put down a bunch of zeros. And you can even ignore this row of all zeros. It does nothing. And then just remember to do the extension and shift right. All right. So for a 3-bit multiplier, here with this algorithm, we need 4 steps. Right? 1 step for each bit plus that extra luggage. Right? So 3-bit multiplier, we took 4 steps. And we can do better. We can always do better. Right? The theme of this course, like I mentioned 3 topics that we're going to talk about in this course: design, analysis, and optimization. And this is the optimization part. Right? We can do better. I don't want to spend 4 steps. I want to spend 3. 3-bit multiplier, do it in 3 steps. And the way we can do it is, again, by looking at these positional weights and the actual luggage. So for the 2's complement negative number, this is the actual luggage. And originally, in that 3-bit, 4-bit number, the most significant bit has a positive positional weight, right? Just like a regular unsigned. But these 2 numbers can be combined. If you add them together, right, b to the n minus 1 plus, or I should say minus, b to the n, it's essentially negative b to the n minus 1. 8 minus 16 is negative 8. Right? 4 minus 8 is negative 4. So what you can do is you can think of this actual positional luggage as something that can be embedded into the positional weight on your original MSB. And now your MSB would have a negative luggage, a negative positional weight instead of the original positive positional weight. Right? With that representation, you no longer have to worry about the actual luggage. The negativity is embedded to the MSB of the original number. Again, looking at this very simple number, 101, from the original actual luggage view, we have 1 plus 4 minus the luggage 8. But with this embedded view, you can just treat this as 1 minus 4. Right? A different way to break down the magnitude of a negative number by looking at individual positional weights. Right? What this allows you to do is to do a multiplication in 3 steps for a 3-bit multiplier. These 2 bits would have positive positional weights. The last bit would have a negative positional weight. So 3 steps, the exact bit width of a multiplier, you can do multiplication. Again, we still need to handle the shift and extension by following the sign. So this will be sign extension. When you do shift, we simply put down zeros. And now if you do everything together, this is what you get. Right? 3 steps, 1 step for each bit in the multiplier. Just remember that for the MSB, you do a subtraction because it can be viewed as having a negative positional weight by embedding that actual luggage onto its original positional weight. Any questions? All right. So what about 1's complement? Again, just for comprehensiveness, talk about 2's complement multiplication. Right? 3 problems we need to handle: how to shift, how to extend, and how to handle the MSB. Those are the exact same 3 problems for 1's complement multiplication. Right? So let's take a look at this number. So let's say if my number is 0, 1, 0, right? If I want to shift it, essentially I want to multiply this number by some powers of 2. Right? That's what shifting does. So what do I get? Well, if I want to get 4x, I just do 0, 1, 0, and then put down 2 additional zeros. Right? So this is the original number, number 2, 2 times 4. Right? I do get an 8 in 1's complement. What about for a negative number? 1, 1, 0. OK, 1, 1, 0 is negative 1. Right? Simply flip it. That gives you the absolute magnitude. Negative 1, if I want to multiply by 4, I'm looking for a negative 4. Right? Negative 4, I can write down 4 first. 0, 1, 0, 0. And if I want to negate it, I got 1, 0, 1, 1. That's negative 4. 1, 0, 1, 1 is negative 4. Or you can think of this as 1, 1, 0, 1, 1. Right? So 1, 1, 0 is the original number. But now we're shifting in 2 additional 1s to make it negative 1 times 4. So to multiply a 1's complement number by a power of 2, right? Multiply something by 4, by 8. When you do the left shift, you have to shift down the sign. Right? Positive number, you're shifting more zeros. Negative number, you're shifting more 1s. Right? Do I know these rules beforehand? I don't, right? But by trying out one positive example and one negative example, you can easily derive the rules. All right. Now the question is how to do extension, right? 3-bit number, same magnitude, fit in 5 bits, 6 bits, and even more bits. So 0, 1, 0 in 5-bit format. You can put down more zeros, essentially more signs. For 1, 1, 0, if you want to make it longer, again, you do sign extension. Right? This is negative 1. This is also negative 1. This is 2. This is also 2. Right? Same magnitude but longer by doing sign extension. So essentially, for 1's complement, whether you do extension or shifting, you always put down the sign. Right? It's kind of even easier to remember than 2's complement. And then implicit luggage, we'll see that in 1 second. So for 1's complement multiplication, the implicit luggage will be negative 7 for a 3-bit number instead of negative 8. And negative 7 is kind of very hard to handle. 7 is not a power of 2. So you cannot easily calculate multiplicand times 7 by simply shifting the multiplicand. And what we got to do is we got to break down that number into some powers of 2. Negative 7. OK. Negative 7 can be interpreted as, oh, this one is actually already after the simplification. Give me 1 second. Right. Remember, for a 3-bit 1's complement number, like 101, 2 ways of interpreting its magnitude. It's either 1 plus 4 minus 7. Right? That's one way according to the actual luggage. Or it could be you can embed the actual luggage onto the positional weight of the most significant bit to treat it as a negative 3. So 101 can be read out as 1 minus 3. Right, again, we're embedding the actual luggage onto the positional weight on the MSB. Negative 3 is also kind of hard to handle in the multiplication algorithm. Right, it's not a power of 2, so you cannot simply shift the multiplicand to get that magnitude. What you have to do is you have to break it down into some approximates of powers of 2. Right? Negative 3 is negative 4 plus 1. Right? Similarly, negative 15 is negative 16 plus 1. Negative 31 is negative 32 plus 1. Right? Break down this number that is not a power of 2 into 2 powers of 2. And this allows you to simply shift the multiplicand to make the computation happen. Again, for the 3-bit number, I need to handle this one. Right there, color-coded, so kind of easy to see. The purple one, that's one copy of the multiplicand. The green one, well, that will translate into negative 3 copies of the multiplicand. But negative 3 can be broken down into minus 4, then plus 1. So you shift the multiplicand by 2 positions, multiply by 4, and then add 1 copy back. Right? These 2 steps together will give you a -3 times the multiplicand. And the question remains, right? How do we do shift? How do we do extension? We do sign shift and sign extension. So for any number that are negative, I put down 1s over here. The middle number is positive, sign extension, sign shift. Next number, that's a negative number. So when I do that shift, right, multiplicand times 4, I need to put down more 1s. And that is exactly what I need. The original number is -1. This number is -4. And then this one will be we add 1 back. I mean, if you think of this as already having the negation, this one is like a minus -4. And then I want to add 1 copy back. And again, let me just fill out these additional extension bits. We do sign extension, sign shift. And eventually, now it becomes a task of doing those a bunch of binary addition and subtraction. And this is what you will get. -1 times -2 gives you a 2. So we essentially spent over here 4 steps. But it's really 2 steps for these 2 bits of the multiplier, and 2 steps for the most significant bit, which has like a positional weight that is not a power of 2. So we have to break it down into 2 steps. All right. Any questions about this? So to sum it up, again, all of these algorithms, addition, subtraction, multiplication, right, the correction rule, those are driven by the positional weights. 2's complement has an actual luggage. 1's complement has like a smaller negative luggage. And what you can do is you can sort of merge these 2 numbers and put the combined positional weight on the MSB. That will save you 1 step in the multiplication algorithm. And this is what you get, right? Negative positional weight for the MSB, negative positional weight plus 1 for the MSB. All right, so we have seen addition, subtraction, multiplication. What's missing? Division, right? Division is the one that's missing. And this is, again, for your curiosity. Division is doable. It's a little bit more complicated. Essentially the same as decimal division. You try to line up your divisor with some of the upper digits of your dividend and see if it fits. If it fits, you do a subtraction. If it doesn't fit, you drop down 1 additional bit from the dividend. Right? So at every step, you can do sort of like a comparison. If the divisor is smaller, you do a subtraction. If divisor is greater, you don't do a subtraction. You drop down 1 more bit and do a comparison on the next step, and then selectively do a subtraction. Right? Subtraction if divisor fits into those partial bits from the dividends. Same as decimal division. But you see, one of the reasons why we are still spending this much time talking about binary addition, subtraction, multiplication after we have learned decimal arithmetic so well is because there's some hardware-related optimizations that we're trying to achieve, right, in terms of how we represent numbers and how those numbers get into the computer hardware to be executed by a regular binary adder. For division, there's also a similar goal. You can do a bit of optimization. Instead of at every step, compare, subtract, compare, subtract, what you can do is you can do subtract first. And then if you find that, well, subtraction gives you sort of like an overflow, that means you overdid it, right? You couldn't really subtract. Then you do a correction, right? This allows you to, in the best case, do a sequence of subtraction to make things work, right, without needing any comparison. In the worst case, you're not really doing any worse than the regular algorithm, right? You can still do the correction after you have subtracted. So instead of correction followed by, instead of comparison, subtraction, comparison, subtraction, you can do subtraction and sometimes correction. subtraction, sum times correction. You can even do better by just doing a single step for each bit in the dividend. And then, again, I'm going to skip it. And this is only for your curiosity. Ideally, you only need one step to handle every bit of the dividend. And all of these optimizations are necessary to achieve efficient computer hardware. Right? The way we like to think about the problem is sometimes different from the way computer likes to think about it. Right? We have different optimization goals. We like some intuitive solution, but computer likes some mathematical or binary manipulation to make this computation happen fast. So with that, we have really covered everything about binary arithmetics. Unsigned 2's complement, 1's complement, addition, subtraction, multiplication. And then we have also navigated through many of the hardware-specific challenges, like how to handle overflow, what are the range of the numbers that we can represent, how to do extension, how to do shift, and multiple views on the positional weights, embedded, actual, right? And they give you different optimality characteristics when it comes to multiplication algorithms. And for 1's complement, correction, and even more. Right. So I would like to take a pause and congratulate you for learning everything about binary arithmetics. So how do you feel? You feeling all right? Yeah. Any questions about many of these things that we have covered? Again, by the way, don't worry too much about 1's complement multiplication. Right. Other than that, all the other things are pretty important. Yes.
So all the three just learn which ones are.
Unsigned 1's complement, 2's complement times addition, subtraction. Unsigned 2's complement times multiplication.
Do we not need to know?
1's complement multiplication.
That's the only thing. What about division?
And all the purple slides, like division, you don't have to worry about it.
Oh, okay.
Yeah. So these purple slides, you see there's like a very faint writing over there, like for curiosity only.
Oh,
Yeah, it's probably more visible when you download the slides. All right. Yes. Okay.
Do we need to know anything related
For decimals, what do you mean?
do we need to do like decimals?
Sort of, I assume. Well, you don't have to, but the thing is, when you do this binary operation, it's always good to just write down the decimal counterparts on the side to verify your result. But I mean, it's not going to be more than like 2, 3 digits of binary decimal numbers. Yeah. On the right side of the decimal point, I see. OK, so what we have learned over here is called fixed point representation, which means we essentially assume right now, based on this scheme, we assume the decimal point to be on the right of the 2 bits. Right? So if you have a decimal point, all the arithmetic will work the same way, except that you align them up according to the decimal points. But you don't have to specifically worry about that. So with that said, we're going to move on to a different topic. It's called binary codes. And this is really motivated by one of the challenges that we observed when we did base conversion. Right? From decimal to binary, sometimes a terminating decimal number becomes a non-terminating binary number. And you really cannot store this number with full accuracy in your computer memory. Right? Have a fixed width, 32-bit, 64-bit. And you just cannot support some kind of repeating numbers. Right. So this is a problem for the kind of binary representation that we saw. It's also a problem for floating points with exponents, mantissa, that sort of stuff. If it's non-terminating binary, it will be non-terminating in any kind of binary representation. And there are many situations we don't want to live with errors. I would say for industrial and scientific computation, you don't want to live with any error. For financial, when you're dealing with money, you don't want to live with error. For defense applications, again, you need high accuracy, and you don't want to tolerate any error. Right? For these kind of situations where you cannot tolerate errors, there's a solution, and the solution is called binary codes. Instead of representing that full number as a binary number, you represent every digit as a binary coding, a way to encode each digit into a binary string. And this binary string, right now, you see this is 01106, 0011, 01015. Right? It's according to the kind of regular binary representation for each digit. But you don't have to follow this kind of positional weights. You can define arbitrary binary codes to encode different digits. Right? Think of like ASIC2, when you type on the keyboard and those are converted into binary numbers. Or when you're browsing the website, you're trying to download the file. They are not encoded in this kind of binary format, not in the binary number, but in some arbitrarily defined binary codes. Right? So you can define any binary number, binary representation for any digit, and then encode an arbitrary sequence of letters, numbers, whatever you like, using binary representations. And since every digit has a precise binary code definition, we can maintain full accuracy. Right? Even though a little bit more storage, but we can indeed maintain full accuracy. And it turns out that we can still do arithmetics with binary codes. There are a few different binary codes. These are from your textbook. We have 8421, the more standard way of encoding every digit based on its binary representation. We also have like 6311, right? Different binary codes with different positional weight definitions. And that's more or less an arbitrary definition. You could do 6311. You could do 6321. You could do 6211, and whichever you like. Right? 6211 is probably 6211 is actually also fine. Yeah, so there are many possibilities. You can arbitrarily define those positional weights, and then as long as you make sure that when you add up the positional weights, right? Like let's say 111 over here, that gives you a 5, and then that's valid as long as you can represent all the numbers from 0 to 9. Right? It's cool. And the XS3 is essentially starting from BCD, but you're adding 3 to each representation. So 0 is represented by like unsigned 3. 9 is represented by unsigned 12. Right? 7 is represented by unsigned, what is that? Unsigned 10. Right? Everything is added by 3. And again, you could define it in whichever way you like. You don't even have to define any specific rule. You can just assign a random selection of binary codes to these numbers. But as it turns out, what we care about the most would be this one and a little bit this one, because you can do arithmetics with these codes. And arithmetics are particularly beautiful for XS3. Right? 6311 is only like knowing that we can do arbitrary positional weight assignment. And then the other two codes, they have their own purposes. So 2 out of 5, this will eventually be useful for error detection. And gray code really tells us a concept where these adjacent numbers, they only differ by 1 bit, right? Differ by 1 bit, differ by 1 bit, differ by 1 bit, et cetera, et cetera. Right? This kind of distance relationship, we'll carry them more later into the next week 2, 3, and 4 of the class. We're going to see a lot of this, how this adjacency or neighboring relationship between binary numbers can be used to optimize the implementation of digital circuits. That's a really important principle called Hamming distance. But we'll see more of that in the coming weeks. Right? For now, let's just worry about the 2 ones where we can do arithmetics. Right? Since we're talking about arithmetics. 8421, the kind of regular binary representation, and XS3, where everything has been preloaded with an additional 3. All right. So 8421. The idea is to encode every decimal digit into 4 binary bits. Right? And here, 1 is represented by 1. 5 is represented by 5 in binary. Right? Similarly, 2 and 2 at the bottom. And as you can probably already see, the way we do binary addition is simply just doing the binary calculation digit by digit. Right? But every digit consists of 4 binary bits. So we sort of handle addition within those 4 binary bits. So this would be 1110. That is 7, right? Which is correct. 2 plus 5 is 7. Next digit, 0011, which is 3. Like it's trivially correct. No complexity has happened. It works perfectly for arithmetic. Let's try another example. All right. So 5 plus 7. So this is 1, 1, 5, 1, 5, plus 2, 7. Right? Another decimal addition example. But if I follow the binary addition rule, let's see what we get. We get a 0, the carry, 0 with a carry, 1 with a carry, 1. Next 4 bits, 1, 1, 0, 0. All right, so what am I getting is, I'm getting a 3 over here, which is incorrect. I'm getting this crazy stuff over here, which is even more incorrect. It's not even a valid digit. Right? Based on this definition, I can only represent digits from 0 to 9. And this one is just too big. It's like 12. It's more than what I'm using. This is invalid. Do you know why it's invalid? Any ideas? Yes? Yes, yeah. We're using 4 bits, right? And there's a bit of unused regions over here until 15. And all of those representations do not correspond to any decimal digits. But in binary addition, they could still happen. Right? That's where the problem arises. And if you really want to solve it, you can solve it. Right? You can compare this number with 9. Right? See if it's greater than 9 or smaller than or equal to 9. And then make some correction step over here. And then if it's like greater than 9, you can generate an additional carry to the next digit position, and then use that for the next 4 binary bits addition. A little bit complicated, particularly when you're trying to compare this number with 9 and then deciding so many rules. It's requiring more hardware in computer system. It's also incurring additional delay. Right? This carry chain, the carry sequence from one digit to another digit, that's usually the bottleneck of addition operations. Right? That's the case for decimal. That's also the case for binary. And having so much things to check before you can generate the carry is also elongating the computation duration or the latency. And that's the reason why we use XS3. XS3 is a very elegant solution to that problem. Right? You may think it looks weird. Every number is not represented by the regular binary, but it's rather represented by that binary number plus 3. Right? But let's see what we get from this problematic computation. Right? Again, now I'm also adding together 1, 5 with 2, 7. But everything is represented by XS3. 2 and 7. Right? You can think of these numbers as based on that table, or simply the magnitude plus 3, or the 7, sorry. Right? The magnitude plus 3. That's the binary representation. So let's see what we get. Right? We get 0, 1, 0, 0 with like a carry out. Right? With binary addition, I get a carry out. And that's actually what I need. I need a decimal carry out from 5 plus 7. And I do get a carry out in binary computation. And this carry out can then be directly consumed by the next bit or next digit. So what I get is 1, 1 gives me a 0, carry of a 1. 1, 1 gives me a 0, carry next bit a 1. All right. Yeah. Take a moment and see what we are getting over here. This one, is it correct? No. Why is it not correct? Exactly, right? 0010 is not a valid representation. The smallest I can use is 0011. Well, I do need a 2, but I need 2 being represented in the same representational scheme as my inputs. So this one, if I need a 2, I really need to get a 0101, right, based on that table, 0101. This is what I expect. And for the next digit, what am I getting? Well, I'm getting, I need to get a 4, right? I should get a 4. I should get a 0, 1, 1, 1. So these are my expected value. But what I got is incorrect. I got 1, 0, 1, 0. And if you compare the difference, 0, 0, 1, 0 is off with the bottom number by positive 3. 0, 1, 1, 1 is off with 1, 0, 1, 0 by negative 3. So in exercise 3, after you have followed the binary computation, the kind of the sum for every digit is still incorrect. You have to do some additional correction. But what this allows you to achieve is really the correspondence between binary carry and decimal carry. Whenever you have a binary carry from a 4-bit computation, that would indicate exactly you have a decimal carry. So this binary carry can be consumed by the next 4 bits to make future computation happen. Essentially, once you complete this bit, you can directly jump into the computation for the next bit without those additional handling and processing resource. But within each bit, or actually within each digit, you have to do a correction step, depending on whether or not you have the binary carry. When you have a carry, you do a correction by adding 3. When you do not have a carry, you do a subtraction by 3. So within each bit, there's still some additional correction step required. But between 2 digits, right, carry can happen really fast. And overall, this will give you a faster computation. Carry chain, the dependency between one digit to another digit, is the bottleneck of addition. And this one solves that bottleneck by building the equivalence between binary carryout and decimal carryout. Again, we're never here to just learn the rules. We're trying to figure out why. And the reason is because BCD, or the 8421, the regular binary representation, they only use this early part of the representational range. And when you add together two relatively big decimal numbers, you might fall into this region, right, the invalid region. It's very hard to tell that because you have to check for many things. You have to check your number against 9 by running a comparison, which is pretty resource intensive. In exercise 3, we're creating some access region before and after the representational range. So before 0011 and after 1100, those are unused. And in terms of the representation of a number, let's say 3 and 7, or essentially any digit, every number has been preloaded with 3. Right? 3 is represented as an unsigned 6. 7 is represented as an unsigned 10. Everything in terms of their binary representation has been preloaded with 3. And we add together 2 numbers. Right? The result will have 2 copies of that access. Right? You can think of this again as some extra luggage of 3. And the result would have 2 copies of this luggage or access. And when you have a decimal overflow from 1 digit, right, or decimal carryout, your magnitude will add up to 10. And with these 2 additional copies of the access, that will jump up your binary representation to 16 to produce a binary carryout. So the access of 3, by observing the difference between your representational range, which is 0 to 16, and the numbers that you're trying to encode, which is 0 to 15 and 0 to 9. Right? So 16 and 10 numbers differ by 6 numbers. When you preload each of your 2 input operands with a magnitude of 3, eventually we can fill in the gap and ensure that binary carryout equals decimal carryout. Any questions? Does this visualization make sense? The kind of this rosy color, that is the magnitude. The green color, that is the access. Add together 2 copies. The result has 2 copies of those access. And that fills in the gap between decimal, which is 10 numbers, and 4-bit binary representation, which is 16 numbers. And by filling the gap, I mean if the number is big enough, when we have a decimal carryout, the binary representation will also have a binary carryout. All right. So the last thing I want to show is how to do subtraction in XS3. I'll give you 1 minute to work on this exercise and see if you can find out the subtraction correction rule. Again, 25 minus 17. Try to do the binary subtraction bit by bit and see what you get and what you expect. Okay, 1 minute timer starts. Actually, I'll give you 1.5 minutes. All right, time's up. Let me just work with you together through this example on the board. So first I'm setting my expectation at the bottom. I just put down my expectation. That's essentially what I should get at the end of correction and all the binary calculation. And then when I actually do the binary subtraction, I got 0, 0, 1, 1, 1 with a borrow. Right? So I will just bring that borrow into the next digit and then make the 4-bit binary subtraction, which gives me 0, 0, 0, 0. And for the rightmost digit, I need to do the correction by minus 0, 0, 1, 1. Second digit, I need to do the correction by plus 0, 0, 0, 0, 0, 1, 1. Right? That's how we figure out the correction rule without knowing it. Right? By running the binary calculation, by setting up the right expectation, you can reverse engineer the rule. Right? I didn't tell you the rule, but if you follow this procedure, you can figure it out by yourself. So to sum it up, addition, if there's no carry out, right, which means you're still within that digit, but then having 2 copies of the excess is too much, so you need to subtract 3. Subtract away 1 copy. If you have an overflow, you have already used both copies of the excess to jump through the gap between this digit to the next digit, so you need to add 3 back. Subtraction is just the opposite. So this idea of XS3 has another property, which is the symmetry. The symmetry between, let's say, 0 and 9. Right? 0, 0, 1, 1, 1, 1, 0, 0. They are symmetric. And what this allows you to do is really you can do subtraction without using subtraction. You can convert some subtraction operation, A minus B, as a bunch of complement operation together with addition. So if you expand this formula, this is actually exactly the same as that subtraction. But now, all the subtraction becomes 999 minus 1 of your input operand. And in XS3, subtracting a number, a 3-digit number, from 999 is essentially flipping all the bits, because each individual digit can be flipped by just flipping all the bits. Right, so a quick example of where we can make use of these properties in decimal operations. So to sum it up, we talk about one's complement, addition, subtraction. We talk about multiplication for regular unsigned binary, 2's complement and 1's complement. We also show binary codes, which is a way to preserve full accuracy. But still, with things like XS3, you can make arithmetic happen pretty easily. And finally, talk about addition, subtraction in XS3, and also the corresponding correction rules. So that's everything for today. I look forward to see you tomorrow. Hey, Max.
Question.
Yeah.
So I joined late, right?
Yes.
Okay, so here's the thing, right? Can't you turn everything like this weekend or the latest 3 days? Just on Monday and Tuesday.
Yeah. Yeah. By I can definitely get you some information.
So I have a kind of watch it.
Since Monday doesn't have the real work for Monday, Tuesday, that's the first one. Today is the second real work. So these two are supposed to due on Tuesday and Friday, like so Thursday and Friday respectively. So I can do it next Sunday. And the Thursday will be the regular deadline. Oh, I see. It will be week 3, Tuesday of week 3.
Okay.
Yeah, I can get you the date.
And the finals on Friday? Like
Finals on Friday, the Friday of week 5. Yes, yeah. But it's more like a survey, like a competition question.
Okay, so I just have to scan it in the...
Yeah, you can just watch the recording of podcast, yes. And then you can access the workbook on Canvas. Did you get access?
Oh, I didn't enroll it. I'm going to enroll after class.
Okay. I can send you the first several.
Extension on workbook.
Yeah, I can give you extension for the first 3 workbooks, essentially Monday, Tuesday, and Wednesday, until the end of Sunday.
Yeah.
You're gonna enroll right now? Yeah. All right. Friday morning.
And the Thursdays we could do on Monday.
Thursday is like a logo. So around today's to be due on Friday so that we can grade them on Friday, give you the feedback, and then you can bring that feedback into the yeah, we have discussion today. Yeah, our discussion led by our PA audience.
So, like, we're learning about 2 topics right now. So eventually, are we gonna learn about like registers?
Yeah,
Is
so
that lecture already going?
so we're gonna continue with adder design. So after this, after we talk about binary numbers, we'll talk about Boolean algebra. The kind of 0 sum 1 and gate or gate XOR, and then we'll try to build some components, including adder, the adder subtractor. And we're gonna see at that point how we actually implement the overflow detection logic, how we convert a regular adder into a complement adder. And towards the end of the class, we're gonna see how to design registers, and then put that together with adders, subtractors, to realize more complex arithmetic computations.
Oh yeah, so on the exams and stuff, like, are you doing like a design exam or like, are you like, what's the exam? Is it like, is the exam question like, oh, you add 2 numbers, like write it out in the binary code for the...
No, example question would be something like this, right? Very conceptual questions. Things like, we learned about access 3 for decimal.
Yeah.
If you apply access 3